Hi, my name is Thushara. Reservoir cascades are operated for multiple purposes by balancing variable demand and supply. Among many uses, agriculture and hydropower is common in many instances. For the reservoir water releases, most of the time we need to consider asynchronous demands of hydropower and irrigation, these trade-offs in the operational rules. When deriving these rules, we also need to consider uncertainty of the inflow as well. The objective of this study is deriving reservoir cascade operation policies considering uncertainties and trade-off among the multiple objectives. Multi-objective evolutionary algorithm has been used to discover the operation policies, but calculation burden is a challenge. The objective of our study is deriving these operation policies with less calculation burden. So we use stage-wise optimization. We illustrate the method through Mahaveli Multipurpose Reservoir of Sri Lanka, which mainly used for hydropower generation and irrigation-based agriculture. Cascades spread through several river basins, and there are water allocation decisions among competitive users in several river basins. Among them, Polgolla is really important, which divert large amount of water to dry northern part of the country, mainly for irrigation purposes, which avoid hydropower generation of the downstream river basin. This cascade used for 2 agricultural seasons, 6 months each. So the goal is finding 21 reservoirs and 7 water allocation decisions, operational rules under uncertainties and trade-offs. So it is really calculation burden. So we use stage-wise optimization. First, Kothmale and Polgolla as stage 1, and then downstream Victoria and Randhanigala as stage 2. The first step of multi-objective evolutionary optimization is defining objectives, identify decision variables, and the decision space with constraints. Evolutionary algorithm, multiple objective and algorithm of MATLAB optimization toolbox, which is based on NSGA2, is used for this study. It is required to calculate the objective function for the generated population. For this purpose, we use simulation model of the cascade, which is based on system dynamic approach for 1000 years of inflow data to represent the uncertainty of the inflows, and we selected last 10th percentile to show the climate extremes. Using NSGA algorithm, we derived the trade-off frontier. In stage-wise trade-off frontier, you can see the range of energy and yield. Of course, the highest energy corresponding to the lowest water diversion to the north. But if we selected middle point, the corresponding operation rules of the Polgolla and Kothmale we can derive. By fixing these values, we can move to the stage 2 and find the trade-off frontier, which leads to the stage 2 Victoria and Randhanigala operation rules. Operation managers, water managers can use these trade-off curves to derive these operational rules looking at the trade-offs among the objectives. And this method can be used for other reservoir cascade, which used for different multiple objectives as well. I would like to acknowledge National Science Foundation and several Sri Lankan organizations who support for this study. Thank you.